For the following system, we want to find the fixed points and stability of it. Now, the first step that we have to do is we have to find our x variables. And for that, what we have to do is essentially take the highest number derivative of every single variable in our system and add them up. So let's write that out. So we'll essentially have number of x variables needed. That is going to be equal to the number of the highest derivative of y, so we have a y variable, plus the number of the highest derivative of x. So looking back at our equation and looking for the y's, so we see that's going to be the highest order derivative that we have. And y is just going to be to the first derivative. So we're just going to write down 1. And then for x, the highest order derivative that it has is 2. So we'll just write down 2. So that means we're going to need a total of 3 x variables to describe our, essentially our system. So we can start out by writing let x1 be equal to something, x2 equal to something, and x3 also equal to something. Now x1, that would be easiest if we made it x1, or excuse me, x. And if we said x2 was going to be x dot and x3 would then be y, because we still have to include y. And now notice that we don't have any x double dots defined as one of our 3 x variables. And the reason for this is because we want to try to make this system as simple as possible. And by putting another x double dot in there, we're essentially reverting back to our complex, nasty system up here. So we want to try to avoid that. So now that we have our x variables defined, we can then substitute it back into our original equations. So we said before that x3 is equal to y. Well, up here we have y dot for that equation. So we'll essentially write out x3 dot is equal to we'll have sine, I was looking at the wrong equation. We'll have sine of 2y, and we said y was going to be x3, and we'll have plus 3u, where u is some external effect on our system. Now for the other equation, we have x double dot, and since we said x2 will be equal to x dot, we'll then say x double dot is equal to x2 dot, and that'll be equal to negative x dot, which will be x2, times y, which will be x3, times cosine of x, which will be x1, plus x, which will be x1, minus u, which again is another external effect on our system. So now, the first step that we want to follow after defining our x values is we want to convert it, or convert our equations to standard form. Now, essentially for x2 and x3, they're pretty much already there. This is really for our x1 dot equation, because now we have x3 dot represented, great. We have x2 dot represented, perfect. But we don't have anything to represent x1 dot in our state space form. So with this, it'd be very easy just to make that relation between x1 dot and x2, because x1 dot is equal to x2. And then for other two equations, we can essentially just write those back out. So nothing too crazy. Okay, so now the next step that we have to do is we have to find our stationary points. Okay, so essentially what this means is we're going to take our x1 dot, our x2 dot, and our x3 dot, and we're going to set those equal to 0 and see what values we get for x1, x2, and x3. So let's do that. So if we have x1 dot is equal to 0, still going to be equal to x2. So right off the bat, we can see that x2 is going to equal 0. And then for x2 dot, so we'll set that equal to 0, and then we'll set that equal to negative x2 times x3 times cosine of x1 plus x1 minus u. And then for x3 dot, it's going to be equal to 0. It's going to be equal to sine of 2 times x3 plus 3u. So right off the bat, so we said x2 is going to be equal to 0. So that means this is going to be equal to 0, so that term will actually drop out. Now, when we're also in our stationary point form, when we're trying to find those x1, x2, x3, a part of like the stationary position, so no movement, we'll actually drop our external effects. So that means our u values will actually go to 0 here. So that means in our x2 dot equation, we'll get that x1 is equal to 0 along with x2. But now for that third equation, x3 might not necessarily be 0, but we have to find out. So we'll essentially have 0 is equal to sine of 2 times x3. And then we'll essentially have that 2x3 is going to be equal to every single theta value that will make sine equal to 0. So there are many options for this. So let's just write a few. So we have negative 2 pi, negative pi, 0, pi, 2 pi, dot, dot, dot. So we'll essentially say that 2 times x of 3 is going to be equal to pi times k, where k is some integer value. So k could be 0, it could be 1, it could be negative 4, it could be 5,000, whatever it may be. We'll just set that equal to k, just to account for all the instances that we could have that potential fixed point. But now since we have 2 times x3, we actually have to divide by 2 real quick. So we'll essentially have x3 is equal to pi divided by 2 times k, where k is some integer value. So that means our stationary points, we can write all those out, and then we have, so our x1 value, which will always be 0 here in our stationary form, our x2 value, which will also be 0 as well, and then we can write out our x3 value, which is pi over 2 times k, and we'll say for a k, that is an integer. And now we actually have all of our stationary points for our system. So now the next thing that we can do is we can compute the linear system at some stationary point j, because we have a lot of different stationary points, because the sinusoid keeps going on forever unless there's some exponential decay or something like that going on. But let's just say there's not, so then it'll essentially last forever. So that j is pretty much just to identify like which one we're talking about. And then since we are working with the state space form, we have to follow our state space format. So that's actually what we're going to be building out right now. We're going to be putting it into the state space form to get our Jacobian matrix, or essentially our matrix A. Now, the Jacobian matrix, that's what holds all of the little, information, little secrets of our system. That's how we actually find our stability points. So what we can start out by doing is we'll actually have to take our system in the standard form, and let's bring that down here, just so it's a little bit easier to kind of go back and forth. We can put that there. Now, for this first part here, we have our vector of our x dots. So we can start out by writing x1 dot, x2 dot, and x3 dot. And now this is going to be set equal to our Jacobian matrix, or matrix A. Now, since this is a nonlinear system, and I should specify why. So right off the bat, since we have our sinusoids here, a cosine or a sine, again, those are going to oscillate. So this is what will mainly make this a non-linear system. So due to this being non-linear, we actually can't use the traditional Jacobian matrix where we essentially pull out our coefficients from our x. Instead, we actually have to do this, this partial derivative format that we have right here. So we have to essentially go all the way through our x dot 1, and we have to essentially take the partial derivative with respect to x1, then take the partial derivative with respect to x2, same thing for x3, and then we go to our second equation, our partial derivative of x2 dot, and then take that with respect to x1, x2, x3, and keep repeating all the way through. And that's because this is a nonlinear system. If it's linear, it makes life a lot easy, but more difficult examples give you more practice, and then we learn. So what we can do is we can start filling in this Jacobian matrix. So if we start looking at our x1 dot equation here, we can take the partial derivative with respect to x1. Since we have no x1 in it, we are going to end up having a 0. Then we can take the partial derivative with respect to x2. We do have an x2, so we're going to be left with 1. And then same thing for x3. We have no x3 in there, so we'll be left with a 0. There we go. And then let me fill in our x1, x2, x3. That's what this x is for. Essentially listing out our vector of x's. And now we'll take the partial derivative with, or partial derivative of x2 dot with respect to x1, x2, and x3. So from there, we will end up getting x2, x3, sine of x1 plus 1. And then we'll have minus x3, let me move that over a little bit, minus x3 cosine of x1, and then we'll have minus x2 cosine of x1. And now taking the partial derivative of our x3 dot with respect to x1, x2, x3, we get 0, 0, and 2 times cosine of 2x3. That'll be for our stationary point j, so some stationary point. We'll get to that in a second. Now, for our b vector here, now that'll essentially be the coefficients of our external effects in our system. So we can see that the first equation here, we have no u. So that will mean we'll have a coefficient of 0. And then for our second equation, we have a coefficient of -1 for our u, so we'll have a coefficient of -1. And then for our third, we'll have a coefficient of 3. This is essentially figuring out how much this external effect has an impact in that direct equation, or for that specific equation. And with that being said, that's pretty much our entire state space form. So now we can get into the main the main part of this, finding our stability of some stationary point. So we can say evaluate the system at our stationary points. But in this case, we're only going to pick one stationary point because there are many stationary points. Because again, we're working with a nonlinear system that has sinusoids, so we'll have a lot, in fact, an infinite number of stationary points. So we're just going to pick one. So we can say for a stationary point at 0, 0, 0, what we want to do is take our Jacobian matrix, or our matrix A here, and we want to input our values for x1, x2, and x3. So A will be equal to, so our first row here, that's not going to change. We're going to have 0, 1, and 0. Nothing too crazy. But for our second one here, we have x2 times x3, and then those are both 0, so no matter what, we're going to have 0, and then we're going to have plus 1. So 0 plus 1 will be left with 1. And then for these two, so x3, that'll be 0, so that'll be multiplied by 0, and then x2, that will also be 0, so we'll just have 0, 0 here, and then in the third row, so we'll have 0, 0, and then here, so x3 is going to be 0, so cosine of 0, that's going to be 1, 1 times 2, so we'll be left with 2. Now, the way we find our stability in a system is we essentially find the eigenvalues of our Jacobian matrix. So going back to our linear algebra days, we find our eigenvalues by taking the determinant of the matrix A and subtracting by lambda times the identity matrix. So we'll essentially have the determinant of negative lambda 1, 0, 1, negative lambda 0, 0, 0, 2 minus lambda. And then now we can start to solve for our characteristic equation. So we'll have negative lambda, and then what we'll do is we'll multiply by negative lambda times 2 minus lambda, and then minus 0. So the 0 we're not going to really care about too much. And then minus lambda, and then we'll have minus 1, so we'll start at this point, and then we'll essentially have 1 times our 2 minus lambda minus 0. Or we'll essentially just have 1 times 2 minus lambda. And then for the last part, well, we're going to have 0 times essentially 0 minus 0, so it's basically just going to be 0. So we can start to FOIL this out, so we'll have 2 times lambda squared minus lambda cubed minus 2 plus lambda, and that's going to be equal to 0. So now we can try to simplify it. I'm just going to multiply by -1 to make this just a little bit nicer to look at. So we'll have lambda cubed minus 2 lambda squared minus lambda plus 2 is equal to 0. Now at this point, there are a couple different ways you can go about it. You can either put this into a root finder, or what you can do is you can take a guess. So off the bat, I guessed that lambda would equal 1 for a root. And then from there, I had lambda minus 1 and then just factored it out. So that you have lambda squared minus lambda minus 2 equal to 0. And then from here, we can factor it out a little bit more. So we have lambda minus 1, lambda minus 2, and then lambda plus 1 is equal to 0. So in the end, we actually get our lambdas to be 1, 2, and -1. So right off the bat, we can say that this system is unstable. So we're going to write unstable system when it's in this stationary point. And the reason for this is, let me draw a imaginary real axis real quick. So if we say this is our real axis and then this is our imaginary axis, let's plot these eigenvalue points. So we're going to have one eigenvalue at 2, we're going to have one eigenvalue at 1, we're going to have one eigenvalue at -1. Now, what we can see is whenever we actually have a positive eigenvalue, so basically anything on this axis, so basically anything on the real axis, that will instantly be a unstable system. And the reason for that is because with our exponential functions, so if we were to convert this using Euler's equation, we'll essentially see that we'll actually get an unstable effect where it'll just grow exponentially all the way up to infinity. So that is why that when you have some sort of positive eigenvalue, that's why it'll be unstable. So that's why we want to try to get all of our eigenvalues to either be on this negative side or have some sort of like complex conjugate pair or something like that. So that's why this would be unstable. Now, there's another point that you could try, and I'll let you all try that on your own because this video is getting a little bit long, but try seeing what the stability of 0, 0, pi is. Now, I'll tell you ahead of time, so it should be unstable as well, but I want you to try to walk through the steps, take the same steps that we did above, and then see if you get unstable, and then see if it makes sense why it's unstable. So, with that being said, we found the fixed points of an initial system, and then after we found the fixed points, we put the system into our state space form, and after it was put into our state space form, we then solved for the stability around a stationary point. So with that being said, that is all for the video, and I'll see you guys next time.